So now once you know this finite map, next topic of interest is that what is called proper maps. So these proper maps are analog of projective space or analog of compactness. So, but to do that, so next object of study is proper maps or proper variety or complete variety. But to do that, I need to say something about what is called closed immersion and open immersion. Right. Okay. Okay. So, and two things I need to do. First is for two concepts I need to introduce. One is fiber products. Another one is this closed immersion and open immersion. So briefly, I'll not define very rigorously what is a fiber product, but fiber product you can think this is more generalization of product. See, we have seen that if x, y in any variety, so you can define what is called x cross y. But you can generalize more, that suppose you have a map x to z and y to z, suppose f and g, then what you can define something called x cross y over z. And what is this? This is a subset here as a set. This is nothing but set of all points x comma y such that f of x equal to g of y. The point is that this subset has a variety structure. In particular, if I take for example, say x to z and z to z, the identity map, then what is the fiber product? What is the fiber product? If I take, so as a set is what? X comma fx, right? X belongs to x. So this is basically the graph of x f, right? This is how you define graph of a function. So now the point is that if f is a morphism, this is a point is that this is a closed immersion. That so proposition first statement, suppose f is a morphism from x to y, then the graph of f, which is point x comma f of x, x belongs to x, is a closed immersion, the closed subset. So what is a closed immersion? Locally it looks like closed subset, because we are in category of pre-varieties. I cannot say it is a closed. So I'll say that this is a closed subset, or the better word is closed immersion. Let's write closed subset for. So you remember that what is called closed immersion and is in fact this is a closed immersion, and closed immersion or open immersion. If you have a map of variety, say you say x to y, this is closed immersion if it factors through injectively, and this is a this map is closed. The image, first of all, that means this map is injective, not only injective, the image is a closed subset. Then you say it is a closed immersion. And if the image is, it is injective, it is not only injective, if the image is open subset, then it is called open immersion. F is called, yes. So this is, I is inclusion map, so I stands for inclusion. And this is, this Z is nothing but the image, and this is isomorphism. So that is how you define closed immersion and open immersion. If it, F has to be always have to be, because otherwise this is a, this has to be isomorphism, and this Z has to be, this Z is inclusion. This Z is a closed subset or locally closed subset in Y. If you work with pre-variety, there is a locally closed subset. If you just work with affine thing, then this is a. So examples, if you just work with affine, so for example, you take V of F or V of some ideal in some AN. This is a closed immersion. But if you take the D of F, where F is some regular function, say over k x1, x2, xn, then this is a open immersion. Both are injective, VA, this is injective, but one is sitting, they, so more generally this closed immersion and open immersion, this is generalization of this closed set and open set. See, closed set is also is a morphism, right, from the closed set to the underlying variety and the under inclusion map. Same thing you can do that if you have a map of variety x to y, you consider just image f of x. If x to f is a isomorphism, this is isomorphism, and fx is a closed subset of x.
All the maps should be trivial maps. All the maps should be trivial maps. P alpha to A.
Yeah, here everything is inclusion, yes, trivial map. But this is a very trivial example, but one can generalize this for the morphism. You say it is a closed immersion if it is isomorphic, x is isomorphic to f of x, but if it is just an open subset also, this df is isomorphic to a df, but that is the open subset, not a closed subset. So how the image is sitting inside the ambient variety. So that determines whether it is a closed immersion or not. Every map is closed immersion or open immersion, right? It is possible. So these are some special maps. So this is some class of morphism. So now the point is that this fiber product, this graph is a closed immersion in X, the product. That is because yeah, this is always the case. For pre-variety. That this is a proposition. Let me write this proposition. That if is map of pre-variety, I mean at the level of pre-variety, I am not going into deep proof of every statement, but I am just stating it here. A map of pre-varieties. Then graph of f. Then you have this. Then you have natural map. See, x to see, you have this x cross or graph of f you have. So graph of f to x and graph of y. So you have this projection map, right? P1 and P2. Now you have this map x to f. This map, the map which you started with, and you take the equality. Then you have a map from the universal property. Universal property will say that x to graph of f there is a map. That you call it some, say, tau of f. Now the point is that if f a map of pre-varieties, then you can think this x inside some bigger space, and this is as a closed subset, as a closed immersion. Then tau of f x to graph of f is a closed immersion. Or more generally, so this is the image is basically the graph of f. So this is, say, x cross y is a closed immersion. So in some sense, you see your Ax inside a bigger space. This sometimes it is very useful. When you want to study this Ax, you find a map from x to y and think x as some closed subset in some bigger space, and there you study how your x behaves. So sometimes you go to a bigger space, proving things becomes easier. So this is how, because this is a closed immersion, so basically they are isomorphic in some sense, right? The image is isomorphic to the x itself, because that's what is a closed immersion mean. That this image you can identify with x as iso, but the image is sitting inside x cross y, right? Huh? Yes. In particular, if you take identity map, then this is just the diagonal map. And you know, diagonal is a closed subset, because we are so okay, I should say varieties. Okay, let's be careful. Your diagonal is closed subset. So let's talk about varieties, projective variety or. Okay. So I'll explain a little bit more about fiber product. So now what you do, instead of this, if you have something x to y and some z to y, you want to define something called x cross y over z, which is a generalization of graph, and that is called fiber product. So basically, set theoretically, this is nothing but sort of all point. Sorry, what I am writing. This is z, this is y, and you want a map. So this is called fiber product. Now many things, whatever morphism we study, if we want to study some map here, so you do the change of fiber by some appropriate maps, so you get this, and the properties does not it does not change. Suppose you want to study something is proper or something is finite. If f is finite, the fiber, this after base change, this thing is called base change. This is changing the morphism to some other space, and this is the property remains unchanged, right? So in particular, suppose x to y, you have a map and you take a point here in y, so that's a closed subset. So now if you do the base change, what you get is a fiber of this point. Set of all points in X which goes to the point Y. So that is how you see a fiber. It is a base change to a closed point. Right. So this is the way this base change concept is very important. You will see many applications. Okay, I will stop here. Next class I will continue.